We now go to the next speaker, Takanobu Taira. Can you please share your screen? And this is
Yeah.
a 20-minute talk, and the title is Complex BPS Solitons with Real Energies. Yeah, please proceed.
Okay. So thank you. I would like to thank the organizers for allowing me to speak in this meeting. Today, I would like to talk about the work I've done with my supervisor. And it is based on these three papers that I worked on with my supervisor, Andreas Fring, and my collaborator, Francisco Correa. Okay, so here's the plan for my talk. I'll begin by motivating why studying soliton in non-Hermitian quantum field theory is interesting. And then I'll give you two examples. One is the Toft-Polyakov monopole, and the other one is the Sine-Gordon kink. In the monopole case, I'll explain why energy is finite, and I'll talk about the topological stability of it. And in the kink case, I'll explain why one should expect real energy. So since this is a PT symmetry oriented seminar, I thought maybe I don't need to go into details, but I added two of my favorite pictures from PT symmetry. On the left is the energy spectrum of Bender-Butcher Hamiltonian. On the right is the celebration of PT symmetry in optics. And today I will talk about the quantum field theory side of this story. And more specifically, I'll talk about the role of PT symmetry for solitons in quantum field theory. So let me begin by advertising that the non-Hermitian extension of Higgs mechanism has already been done, and there's a list of papers worked on this. And also the non-Hermitian extension of Sine-Gordon theory was also studied in this paper. Now in the model used in Higgs mechanism, there's a natural solution called the Toft-Polyakov monopole. And in the Sine-Gordon case, there's a famous kink solution. So on the left-hand side, the non-Hermitian extension was quite successful. So it's natural to think that maybe one can extend this to non-Hermitian case as well. And that's exactly what we did. So the questions I'm going to answer is do complex solutions exist? And if they do they have real energy? And if so, why is that? And why I think this is interesting is because it introduces more possibilities for the solutions. So that were previously ignored because it was complex. Okay, so let me begin by giving you a very quick review of the Toft-Polyakov monopole in Hermitian theory. So you begin with the local SU2 theory. Here's our action, and the field belongs to the adjoint representation of SU2, and the derivative is upgraded to covariant derivative to compensate for the symmetry of the gauge field. And in the middle, you have your Higgs potential. The procedure is the following. You start with the equations of motion. You choose a spherical answer. You insert it into your equations of motion, and you find a set of differential equations, which is difficult, which is not solvable, but you can take this strange limit, often called BPS limit. You can simplify your equation and find a set of analytic solutions. Now, these solutions are the monopoles. But this isn't the end of the story. You also want your solution to have finite energy. And for this, you require, so through Derek's scaling argument, you can show that if the solution converges to a vacuum solution in a spatial infinity, then you can expect your energy to be finite. So this is everything you need to know for now. So let me go back to this action. How I complexified this action is the following. So this, so I took the model I just talked about, and then I added free theory, and then I added the complex coupling between two theory. So phi1, phi2 still belongs to adjoint representation. The procedure hasn't changed. The limit is now fourfold limit because I have more parameters, and I have one extra solution. What's kind of strange is that even though the equations are complex, the solutions are real, which is actually a problem, because if you look at the Derek's scaling argument, our solution is real, However, if you calculate the vacuum of this action, it's complex. So there's no way this can converge to a complex vacuum. Therefore, the direct scaling argument fails and we can't expect any finite energy. And this seems like the end of the story. However, you can save this by utilizing what's called the Dyson map or similarity transformation, which we took from this paper. Basically, what it does is it maps non-Hermitian theory to a Hermitian theory. So this is our real action found by mapping the non-Hermitian Hamiltonian to Hermitian Hamiltonian. The procedure hasn't changed. However, what's important is that notice that solutions hasn't changed as well. So if I go back a slide, this is the solution before, and now this is the solution. So solution hasn't changed. However, if you look at the direct scaling argument, before we had a complex vacuum, but now we have a real vacuum. But because the solution haven't changed, this boundary condition is perfectly well defined. Therefore, direct scaling argument is saved. Therefore, we expect finite energy. Now, this is great, but maybe you might wonder, what about the stability? So when I say stability, well, I'll explain what I mean by stability. But in usual, so the solution we found belongs to a family of solution called BPS solution. Basically, what it is that you can write your energy in this form. So this part usually corresponds to the kinetic term and this part the potential. I think Andres explained this in detail on Tuesday. But you can basically rewrite this like this. And because this term is squared, you say this is positive, so that means this is the lower bound of your energy. And this quantity is actually the topological charge of your solution. This means if you fluctuate your solution, this term is invariant. So this is topologically stable. That's what I meant by stability. However, because we are considering complex theory, this A doesn't need to be positive. In fact, it could be complex, in which case the inequality doesn't make sense. And to save this, you again use the Dyson map. And now you can map your complex theory to a real theory. So everything is now real. So everything just works like normal. So you do find your lower bound. And what's interesting is that BPS solutions also saturate this inequality, meaning this part becomes zero. And this is explained in detail in this paper if you're interested. I won't go into detail today, but using this, you can actually calculate the energy explicitly. So this is our energy for the monopole. And this is topologically stable, it's finite, it's real, everything's great. But is it really real? Because if you look at the parameters, it looks like it can actually become complex. So we decide to plot this. So the orange is the monopole mass and the blue is the gauge mass. So as you can see, it is real in region 1 and region 3, but it is complex in region 2. And region 2 is bounded by these two strange points we call the exceptional point and zero exceptional point. The zero exceptional point is be interesting because, so this is the point where zero eigenvalue states coalesce with non-zero, coalesce with zero eigenvalue states. And this behaves like exceptional point because the corresponding matrix become non-diagonalizable at this point and the two states are coalescing. However, the eigenvalue doesn't become complex conjugate beyond this point. So it's different from exceptional point in that sense. What's interesting is that vacuum radius at this point is finite. So that means spontaneous symmetry breaking takes place, which means Higgs mechanism takes place, which means your gauge mass should be massive, which contradict what we see here. So there's definitely something strange going on here, but unfortunately, this isn't the focus of our talk today. So I won't say any more about this. The focus of the talk is the symmetry. So if you look at the region 1 and region 3, both regions have a solution which has some sort of symmetry. I will explain what I mean by this. But in region 2, the symmetry, there isn't such symmetry between solutions. So we wondered maybe this is the reason why energy is complex in certain region, and in certain region, some region is real. And this is reminiscent of something from PT-symmetric quantum mechanics. And here's the something. So the question is the following. You have a PT-symmetric Hamiltonian, is the energy real? So if you have a PT-symmetric Hamiltonian with eigensystem, you can follow this simple argument and show the eigenvalue is real. So the answer to this question is actually no. And this is because these two conditions doesn't always come together. So the point here is that it's not enough to have PT-symmetric Hamiltonian, you also need PT-symmetric eigenvectors. This message carry over to the soliton story. So what we want kind of is, instead of eigenvectors here, we want solitons here. So we have some sort of symmetry for soliton solution, and we can kind of follow the analog of this argument to show that energy is real. This was already done by my supervisor in 2007. So if you have a PT-symmetric Hamiltonian, and if your soliton is PT-symmetric, then you can easily show that energy is real. Unfortunately, this didn't work for our monopole solutions. So for that, we needed to extend this to include more possibilities. So under transformation, which we called CPT, this is different from a CPT in quantum field theory. This is some generic antilinear symmetry acting on the field, but basically transforms the Hamiltonian to a conjugate with the argument swap. And so let's say this system have two solutions, phi1, phi2, then this transformation maps one solution to another solution. It could be itself, it could be different. What's crucial is that these two solutions need to share same energy. I think Francisco explained this yesterday, but let me explain why this implies real energy. So let's start with the energy of phi1. So CPT maps it to here. Condition 1 implies that it is conjugate. Condition 2 implies that phi1 maps to phi2. Condition 3 implies that phi1, phi2 share same energy. That means the energy is real. So this is the argument. Now let me apply this argument to monopole. So CPT symmetry is preserved in all regions for the Hamiltonian. However, for the solution, this isn't the case. So in region 1, phi1 plus minus corresponds to labeling of the solutions. Phi1 plus minus is mapped to phi1 minus plus, and phi2 is mapped to phi2. In region 3, this symmetry is slightly different. Phi1 is mapped to itself, whereas phi2 plus minus is mapped to phi2 minus plus. And in region 2, we couldn't spot any sort of symmetry of this type. And as we expected, the energy is complex because of this reason. So this is all nice. And you might wonder, can we use this symmetry as a guiding principle to determine if the given solution is physical or not? Physical as in, does it have a real energy? And the question is not really. And I'll show you in detail why, or I'll show you some examples. So there's complex sine-Gordon theory. So I took this example from this paper. So this is the potential part of the action. So I ignore the kinetic term for now. They calculated the Dyson map. It's not easy, but you can calculate it. Then you can find that this is actually equivalent to standard sine-Gordon theory. Now, this complex potential have symmetry, CPT symmetry, which respect the condition 1, that it maps this to a conjugate of itself. Now, if you look at the solutions, because this is equivalent to sine-Gordon theory, you can find that actually this theory contains kink and anti-kink solutions. These are complex kink and anti-kink solutions. And these solutions all share the same energy. And under this CPT transformation, the kink solution is mapped to anti-kink solution. So this respect the condition 2, this respect the condition 3, that means energy is real. We also looked at the 1+3 case, which is the SCAMI model, which Francisco talked about yesterday. But the potential takes the same form. The phi is now replaced with zeta, which is the radial part of the three-dimensional sphere living in the field configuration space. And so this is the radial part of your skyrmion. Now, under this CPT symmetry, the solution is mapped to something which isn't the solution. So you would immediately say, well, the condition 2 fails, therefore energy is complex. However, it isn't, because if you insert this to the energy and calculate the energy explicitly, we did find the energy to be real. So this puzzled us a lot. And we realized there's actually a hidden symmetry that we didn't notice before. So this is not at all obvious that if you do this transformation, this quantity is mapped to conjugate. You can check this. But yeah, I mean, this isn't the first symmetry you would think about. But fortunately, this symmetry does map your skyrmion to skyrmion. So this means the condition 2 is satisfied with this symmetry, and therefore the energy is real. So the point here is that you can't just look at your Hamiltonian and then guess the symmetry. You need your Hamiltonian and your solution to spot the correct symmetry in order to guarantee the real energy. So this was the last point I wanted to convey. So here's the conclusion. So I said that you can find the well-defined monopole solution satisfying the direct scaling argument in the complex theory. And for the Toft-Polyakov monopole, we found the disconnected physical regions. And the reality of the energy is guaranteed by the symmetry of the solutions, the pair of solutions. And the future work, so I didn't really explain this in detail, but Dyson map isn't really unique. This means we would expect our solution to be different. So that could be interesting thing to work on. And also, I didn't really explain in detail what the zero exceptional point is, but I don't actually have a clear understanding yet what this is. So this will be an interesting future work. Okay, that's it for me. Thank you very much.
Thank you, Takanobu. Are there any questions?
Yes, I have a question. It's Uwe here. Yeah, I have a question concerning the figure you had where you have shown these three regions, where we have 1 and 3. Yes, exactly. Is it what's the parameter here? It's hardly visible.
Sorry, this is mu square over m2 square. This is
okay. These are the two parameters in your potential. It's clear. Yeah. Okay.
Yeah, because I took this weird limit where everything goes to 0, but some quantities stay finite. And this is the quantity that survives.
Yeah, it's clear. And when you have such a region, it's somehow reminds when you just compare it with usual phi to the 4 potential. You have these regions where you can where you have in the middle this kind of Mexican head potential, and when you are sitting in the middle, then you have a kind of tachyonic solution. Is this somehow related to this region, or is it not related? Because you have also this mass parameter and the coupling parameter. Could it be related, or is there something completely different here?
So are you asking of if you plot the potential of your variable? Yeah. I'm not sure if it's related because I'm plotting the mass of the gauge field and monopole field.
Yeah.
So I don't immediately see if it's related.
Okay. Thank you. Thank you. Fine. Very nice talk. Very interesting results.
Thank you. Okay. Any other questions?
May I have a related question?
Sure, sure.
On this picture, there are two points, and
Yeah.
because the problem is nonlinear, so the behavior is, as was shown, different. My question is whether there is something like analog of canonical Jordan block representation of any of the related operators, or if it is complicated by nonlinearity.
So I can tell you what I know about this point. So the mass matrix, at this point, so I'm only plotting gauge and monopole masses, but there's also another masses that come in because theory contains many fields, and there's a corresponding mass matrix where at the zero exceptional point the mass matrix becomes Jordan block form. I don't know if that answered your question.
Partially, yes, but it's more complicated in any case. But at least partially. So thanks,
Okay,
thanks for your talk. It was interesting.
Thank you.
Okay, so any other questions? Okay, so if not, let's thank Takanobu for the very nice talk.